Welcome also to the YouTube audience. Our speaker today is Alex McCleary, and he will be telling us about persistent homology for infinite complexes. Take it away.
All right. Yeah, thanks. First of all, I'd like to thank the organizers for putting together this great resource in our field. And so today I'm going to be talking about extending persistent homology to infinite CW complexes. And by the way, feel free to stop me if you have any questions throughout this talk. Okay, so we're going to get, really the idea we're going to work with is really just the classic persistence algorithm, right? The classic persistence algorithm works by computing a diagonalization of the boundary matrix of a filtered complex. And we're really just going to extend this idea. So we're going to extend it to infinite complexes as well. And we're actually going to also use this idea to give us a theoretical foundation for persistence as well. So like right now, the existing approaches to sort of the theoretical foundations of persistence typically lie in two schools. There's like sort of the algebraic combinatorics approach, defining invariants such as the rank function or the birth-death function, and then computing their Mobius inversion to define the persistence diagrams. And there's also sort of the commutative algebra approach of rephrasing things in terms of K adjoin X graded modules, and then using the decomposition theorem for K adjoin X, finitely generated K adjoin X modules. But those two approaches are somewhat lacking in some sense. For one, neither one of them is particularly direct, and they also don't really align with the classical persistence algorithm all that well. And then both of them intrinsically depend on finiteness assumptions. Right? Mobius inversion, you need that finiteness assumption, and same with fundamental theorem of finitely generated R modules over PID. Finitely generated is in that phrase. So to extend persistence to infinite CW complexes, we need a different approach. And so the approach we'll take here is going to be based on diagonalization. So first, I want to start off with a question. What does it mean to diagonalize a linear map? So this is just, let's say you have a linear map between two vector spaces. What does it mean to diagonalize it? And when the domain and codomain of the linear map are finite dimensional, this is not too hard of a problem, right? This is just diagonalizing a matrix. But what about when the domain and codomain are infinite dimensional? Then this question gets a little more subtle. And so the approach we'll take to this question comes from the free functor. So we're going to use a purely category theoretic approach to define diagonalization and build persistence. And so the way this works is we have this free functor. So this is a functor that takes any set and turns it into a vector space by just, the vector space is just all finite linear combinations of elements of that set, right? So it takes any set to its span. And it takes a morphism defined. If you have a function between sets, you can easily extend that to a linear map between their spans. So this is the free functor right here. Let's look at a little example of the free functor, right? So here we have two sets. A has three, so we can think of these sets as bases for our vector spaces. A has three basis elements, B has four, and we have a map between the two sets. The free functor turns this map into a linear map between the spans of those sets. So in this case, it turns it into this linear transformation right here. Or I guess I can, yeah, it turns it into this linear transformation right here. Okay, so now let's look at how we can use the free functor to define diagonalization. So if we have a linear map between two vector spaces, and here these vector spaces can potentially be infinite dimensional, we say that there's this map is diagonalizable if we can choose bases of V and W such that, so if we can choose bases together with an injective function from A into B, such that this diagram here commutes, right? So if we go back to the last slide, here we have an injective function right here. So this is an injective function. And so we're really actually saying that this matrix right here on the right is a diagonal matrix. And that's because we can permute the rows and columns to put this into a diagonal form. From a category theoretic perspective, permuting rows and columns is not really anything significant. They should be viewed as the same with different permutations. So for us, we're viewing this as a diagonal matrix because it's induced by this injective map between the sets right here. Okay, and so really the way you want to think about this diagram here, when you talk about diagonalizing matrices in general in linear algebra, right? You have this, you would have like a matrix here, A, and then you would have two change of bases matrices, like oftentimes what, P and P inverse. And those change of bases matrices are these isomorphisms right here. And then such that this whole diagram here commutes. So this is how we're interpreting diagonalization here. And for finite dimensional vector spaces, I will admit that this is not exactly the definition of diagonalization for finite dimensional vector spaces. We're taking some liberties using this term because we're requiring we're requiring diagonal maps to be induced by injective functions. So these the matrices are always going to have ones along the diagonal and zeros elsewhere up to permutation of the rows and columns. So we're forcing ones along the diagonal, whereas in linear algebra, you typically allow zeros along the diagonal in a diagonal matrix. However, this point is not very significant. I will say you can fix, if you want to fix this and really make this definition truly agree with the finite dimensional definition for matrices, you can replace the category of sets, right? So this is where our bases lie in the category of set. You can replace it with the category of sets with partial set functions. That way you can allow a basis element to map to zero, essentially, by just not defining the function on that element. So if you want to make it agree with the usual definition, it wouldn't be too hard. The thing is, it's not very relevant for us. This distinction is not very relevant for us since the maps we will be trying to diagonalize are always going to be injections. So we'll never need partial functions. We can always find a full function that diagonalizes these. Okay, so moving on. Oops. Yeah, okay. So the domain we'll use for persistence here. So typically in persistent homology, one uses the real line to index filtrations. And that's perfectly fine if you have finitely many cells, but when you have infinitely many cells, you need some means of sort of controlling how things come in. And so we'll use well-ordered sets to accomplish this. So well-ordered sets are, they're really a super convenient thing here. They imply numerous key properties. In this construction, well-ordered sets aren't just used once or twice. They are used frequently and in numerous different ways. So they're actually a very important thing. So let's get to the definition of a well-ordered set. A well-ordered set is just a totally ordered set with no infinite, strictly decreasing sequences. So some examples are the natural numbers, and this sequence right here. So this is the sequence goes 0, 1/2, 2/3, 3/4, etc., converging up to 1. And so we have sort of an upwards limit point, but no downwards limit points. That's the thing with well-ordered sets, is we can't have really downwards limit points, but upwards limit points are fine. And some non-examples of well-ordered sets. The integers are not a well-ordered set, just because the negative integers are an infinite strictly decreasing sequence. And this sequence right here, 1/n, where n is a natural number, is also a strictly decreasing sequence. So, and it's infinite. So this is not a well-ordered set. Yeah, but for our purposes, you can think of well-ordered sets as just embeddings of the natural number. Well, okay. Okay, maybe that's not what I want to say, but the well-ordered sets that will arise in persistence are typically just going to be embeddings of the natural numbers into the real line. Every such embedding will give you a well-ordered set, and that's really what you want to have in mind for this talk, as just embeddings of the natural numbers into the real line. But well-ordered sets are more general than that, and you can have somewhat strange well-ordered sets that can't fit in the real line at all. But that's not so important for this talk. Okay. Oh, is there a question?
Well, I was just going to say, like, when you say embeddings in the real line, you sort of mean order preserving, right? So you can embed the natural numbers in the increasing direction, but not in the decreasing.
Yeah. Otherwise, you could get, for example, like this thing right here, this is a order reversing embedding of the natural numbers into the real line. Yeah, so let's get to the setup we're going to be using for the rest of this talk. So we'll really be interested in sub-level set filtrations. Now, over a well-ordered set, all filtrations are sub-level set filtrations. So this is not actually a restriction at all, or at least it's not an additional restriction after the well-ordered restriction. So what we'll have is a CW complex X script X. So that here the underlying topological space is X, and the face poset is script X. We'll never use the underlying topological space. We'll only really work with the face poset script X. Next, we have a well-ordered set W and a function from our faces into W. And so really, we're going to be interested in the sub-level set filtration of this function here. We're going to fix a homological dimension I and a field K. This is the coefficient field for homology. And then by vec sub K, this is the category of vector spaces over K, including infinite dimensional vector spaces. Okay, so let's get to persistence modules. So for some of you, this will be review, but I'd like to go over it at least in brief anyway. The way persistence modules typically arise is by applying a homology functor to a filtration. So this gives what's called a persistence module. Formally, a persistence module is just a functor from our well-ordered set into the category of vector spaces. But concretely, what this consists of is we have a vector space for each point in our well-ordered set and a linear map for each relation in our well-ordered set. And these linear maps are subject to a commutativity condition, but we're not going to go through that. And since persistence modules are just functors form a category, right? They form functor categories where the morphisms are natural transformations. So this gives us a category of persistence modules. But there are other ways of getting a persistence module from a filtration besides applying homology. And actually, these ways will be more interesting to us for our talk than the homology functor. So, right, the chain space also gives a functor, right? If we take the vector space of I chains of a topological space, that's a functor, right? It gives we get a linear map is induced by a continuous map of topological spaces. So this is a functor. And similarly, we also have a cycle space functor and a boundary space functor. And so really these last two here, the cycle space functor and the boundary space functor, are going to be what's really of interest to us for this talk. Okay, so let's get to free persistence modules now. So free persistence modules are really nice persistence modules. You can really think of them as like vector spaces. The key thing that free persistence modules have is, or the key property they have is that free persistence modules have a basis. So we can build these free persistence modules out of these sort of basic building blocks right here. So we're defining this persistence module here, k to the upset of a. So this is, so here we're picking a point A in our well-ordered set, and we're just saying the persistence module is 0 until we get to that point. And then at that point, it becomes k and continues on forever as k. And a free persistence module is just a direct sum of these types of modules right here. So these free persistence modules are really nice. They have only births and no deaths, essentially. And so, right, we can decompose, or so a free persistence module is really a direct sum of these types of things, of these modules here. But really, the way we index them is with a set, A. Yeah, the set is A, and we have a function alpha from our set into W. So you want to think of the set A as sort of the basis set for the free persistence module. And then this function alpha is telling us where each basis vector first appears. And so we call the pair A comma alpha a basis for the free persistence module F. Okay, so let's look at how we can interpret free persistence modules here. So right, like I just said, the way you kind of want to think of a free persistence module is as like a vector space, except we have this function alpha that's telling us where each basis vector first appears. And we can so we can extend this function alpha. Right now, alpha is only defined on the basis set, but we can extend it to the whole vector space just by, if we have a linear combination, a finite linear combination of basis elements, we can extend alpha to this linear combination by just taking the max of the sort of the locations of each of the basis vectors right here. And if we do this, morphisms between free persistence modules become quite nice. If we have two free persistence modules, one with basis A alpha and another with basis B beta, a morphism between them is nothing but a linear map from the span of A, right? So A, we're thinking of as the basis for a vector space, but we also have this function telling us where each vector happens. So a morphism is just a linear map from those two, between those two vector spaces that in some sense preserves the locations of the vectors. And you can think of this as sort of a condition that we can't map to something that hasn't happened yet. So this says that, yeah, we can only map to something that has already happened. So something that has already appeared, something that appeared at a lower value. Okay, so just like with vector spaces, how sets formed bases for vector spaces, here we have the bases for free persistence modules are sets together with a function from our set to a well-ordered set. And the key concept we used to define diagonalization earlier for vector spaces was the free functor. So that was a functor from the category of sets, which represented our bases, to the category of vector spaces. So we want to do something similar here to define diagonalization for maps between free persistence modules. So that means we want to organize our bases into a category so that we can talk about a free functor. And so we can organize them into a category. The objects are just going to be these bases. So the objects are pairs A alpha, so A is a set and alpha is a function telling us where each basis element first appears. And then a morphism between two of these pairs is just a set function from between the two sets that satisfies this condition here, right? And this is essentially the condition that we can't map to something that hasn't happened yet. Yeah, so an important example for us, a really important example is we've got this sublevel set filtration. And we can look at the chain space or the chain module of F. This is always going to be a free persistence module because we have a sublevel set filtration. And the basis for it is just going to be the set of I chains together with the function F restricted to the set of I chains, right? We know that the set of I chains, like ignoring where things happen and just looking at the set of I chains, a basis for the ith chain space is just the set of I chains. But we also know where each one of those where each I-dimensional cell first appears, right? That's what F tells us because we're taking sublevel set filtrations. So let's see. Yeah, chain spaces of sublevel set filtrations are very naturally identified with free persistence modules. They have, in some sense, a canonical basis. Okay, so now that we have this category of basis vectors, though, we can talk about the free functor. Right, so the free functor is going to be, we're going to map, right, we want to map basis or bases to free persistence modules and maps between bases to maps between free persistence modules. So if we have a basis here, we can build a free persistence module just like this, right? So we just take a bunch of these persistence modules that are 0 until a certain point and then one-dimensional after that point, and we just add them all up. And that'll give us a free persistence module to each basis. And if we have a map or a morphism between two bases, so here we have this morphism eta from A comma alpha to B comma beta. And this is going to induce so just for the moment, forget about alpha and beta. And let's just say eta is just a map between two sets, A and B. This is eta is always going to induce a linear map between the span of A and the span of B. That's just the free functor on vector spaces. This map, because eta does have some extra structure, right? We know that eta, if we go back here, we know that eta satisfies this condition here. So because of that, this linear map up here is going to induce a natural transformation between the two persistence modules. So really, we can sort of reduce the study of free persistence modules down to the study of vector spaces and linear maps between them. They have to work nicely with these functions we have, but we can identify natural transformations between free persistence modules with just linear maps between vector spaces. Okay, so let's talk about one area where well-ordered sets play a key role. So in the category of persistence modules over the well-ordered set W, all submodules of free modules are free. And actually, this is almost an if and only if statement here. You can loosen up the well-ordered condition slightly and prove an if and only if statement. So it has a partial converse. But this is a very important property. And it will have a very important implication for us. So we know that since we're working with a sublevel set filtration, the ith chain module here, Ci of F, is a free persistence module. And the ith cycle module and the ith boundary module are both submodules of that. So because of this proposition here, these two persistence modules are also free persistence modules. And so this is really a key concept for what we're going to be doing. Okay, so now let's get to really what's sort of at the heart of this construction here, which is diagonalizing maps between free persistence modules. And so this is what we'll use to define barcodes for persistence modules. And we'll see that we get some really nice properties out of this. Okay, so just like with vector spaces, how we defined a diagonalization of a vector space as sort of an isomorphism between, I guess we defined a diagonalization of a vector of a linear map as a choice of bases such that we can find an injective map between the basis sets that induces the linear map here. So that's exactly what we have here. Note that iota. So here, this is a map between two bases, but in particular, iota is just a map from A into B that plays nicely with the coordinate functions alpha and beta. So really, this is almost the exact same diagram we had earlier with vector spaces, only we're also keeping track of not just what our basis elements are, but also where they appear. Let's see. Yeah, and so here we call iota a diagonalization of this morphism of persistence modules phi. Okay, and so we get to what's really the main theorem in this project, which is that over a well-ordered set, if we have two free persistence modules, F and G, every injective morphism from F into G is diagonalizable, always. So this is a really nice theorem. This theorem, this is really what allows us to define persistence diagrams or barcodes for infinite dimensional spaces, or not infinite dimensional, but infinite CW complexes. Or you could have them infinite dimensional if you want, I guess, but yeah. So yeah, we proved this theorem with a transfinite version of the usual persistence algorithm. And it's actually somewhat funny because it really just reduces to the classic persistence algorithm, because with really it's a transfinite recursion proof. So it works by right, essentially it's a way to define an algorithm on infinite sets. And so you have two cases. There's a successor case and a limit case. The successor case is where a point has a previous point. And so in that case, you can really just use the classic persistence algorithm to diagonalize it. But the limit case, it actually turns out to be trivial. And it really just boils down to the fact that our free functor is a left adjoint, and left adjoints commute with colimits. So this proof is actually not really any harder than proving that the classical persistence algorithm diagonalizes the matrix. Oh, by the way, one thing I should have mentioned before is that typically when doing the classic persistence algorithm, you don't go all the way diagonalizing it. That's not really an important point though, because the pivots are exactly where they would be if you diagonalize them. So you don't have to go all the way to see what the diagonalization would be. Yeah, and so these diagonalizations are always unique up to isomorphism. So if you take two different diagonalizations, they're always going to be in some sense the same, up to permutations and things like that. And so this is what we'll use to define persistence diagrams for infinite filtrations. So let's get to that. well, I guess, I don't know why I used the word persistence diagrams there. Yeah, barcodes is what I'm using here. But yeah, let's go back to our setting of, right, we have this CW complex X script X. We have an order preserving map F from script X into W. And yeah, now we can define the barcode of F as, what we'll do is we'll take a diagonalization of the map, right? We have the, this is the map we're interested in right here. The ith boundary module of F, including into the ith cycle module of F. And this is always an injective morphism of free persistence modules. So by the previous theorem, we can always find a diagonalization of this. And so once we get a diagonalization of this, really what we'll have is a one-to-one pairing of generators for the boundary space to generators of the cycle space. And this is what's usually called the persistence pairing, right? We're matching up sort of deaths with births in a one-to-one way. And that's exactly what this is doing, right? Boundaries here represent deaths in our homology module, and cycles represent births. So by diagonalizing this, we're getting just an injective function from the set of deaths into the set of births. So that gives us our one-to-one pairing between births and deaths. And so from this, we can define the ith barcode of F as the labeled graph. So we'll use the notation GI of F, G for graph. So this is going to be a graph. The vertex set is going to be, right, B disjoint union Z. So here B is, this is a basis for the boundary space, and this is a basis for the cycle space. And then we're going to put an edge between 2 points whenever a point is paired, right? So for each pairing of points, right? Iota gives us a one-to-one pairing between basis elements of our boundary space and basis elements of our cycle space. And so we're going to put an edge in for each of those pairings. And so, and then we also have the labels, right? So we have these functions beta and zeta, which tell us where these points in our set, in our basis set, occur. And so we'll use those to just label our points. And so this agrees with, or at least in the case when our CW complex has finitely many cells, this coincides with the usual definition of the barcode. But of course, we don't need any finiteness conditions to define this. We're just building it using a diagonalization. Okay, so now we want to get to the algebraic decomposition theorem and show that that holds. So to do that, we'll first talk about interval modules. So this might be old news to some of you, but I'd like to go through it anyway, at least quickly. So if we have a pair of points A less than or equal to B in our well-ordered set W, the interval module K to the A comma B is the persistence module defined as it's one-dimensional if we're between A, or if we're greater than or equal to A and less than B. And it's zero-dimensional if we're outside of this interval right here. And all the maps are full rank. And a really nice property of these interval modules is that these are just co-kernels of the inclusion from K to the upset of B into K to the upset of A right here. The co-kernel of this inclusion gives us this interval module right here. And this is one of the key ideas in the proof of algebraic decomposition. So yeah, let's get to algebraic decomposition now. So this is the algebraic decomposition theorem. It says that if we have this function f right here, and we're looking at the sublevel set filtration of it, its ith persistence module, so just applying homology, the I-dimensional homology to the sublevel set filtration, is isomorphic to here. So here pi 0 is the connected components of the graph. For each connected component, right? So the graph is really the barcode. So every vertex is connected to at most one other vertex. Some vertices, though, are not connected to anything at all. Sometimes in persistence, you pair those unpaired vertices to infinity. Here, I'm just leaving them unpaired. So we're going through every connected component here. So these connected components will either be intervals or just single points. But in either case, we can talk about k to the I. So if I is an interval, this will be the interval module we saw on the last slide. If I is just a single point, this will just be the free persistence module on that point. So in either case, we can define this, and the algebraic decomposition theorem says that this direct sum right here is isomorphic to the persistence module. That is, we can recover the persistence module from the barcode. And the proof for this is actually quite clean, and it's purely categorical and follows just from these facts right here. So the free functor phi is a left adjoint. Left adjoints commute with colimits. Direct sums commute with cokernels. And remember on the last slide, these interval modules are all cokernels of modules. So we can swap the order of direct sums and cokernels just because direct sums and cokernels are both instances of colimits, and colimits commute with colimits. And yeah, interval modules are cokernels. So I'm not going to go through the proof here just because it's a bit too notation heavy for a talk. But it's actually a quite clean proof and doesn't need any finiteness conditions or anything like that. And then the other main theorem we want to talk about here is the bottleneck stability theorem. So first, let's define the bottleneck distance. So here, there's one distinction we're making that we didn't make before. Earlier, we were just looking at maps F from our cells into a well-ordered set. Now we're going to assume our well-ordered set is a subset of the real line. And this will be true in general for persistent homology. So we can define a matching between two barcodes as a graph isomorphism. Because we're working with two functions defined on the same space X, we can get away with requiring matchings to be one-to-one. We don't need to worry about matching things to the diagonal here, just because we're working with functions on the same set X. Yeah, so we can define a matching as a graph isomorphism between the two barcodes. The cost of a matching is then, we have, in our barcodes, we have labels on all the vertices that tell us where they occur inside the real line. So we'll let L sub f is the label function for the barcode of f, and L sub g is the label, L sub g is the label function for the barcode of g here. So once we have this matching, we can define the cost of a matching as basically we look at the difference between points. We have a bijection between points, and so we can look at the difference in the label values between each paired points. And then we can take the supremum over all points. And then we can define the bottleneck distance as a matching that, we can define the bottleneck distance as the infimum over all matchings of the cost of the matchings. Okay, and then we can get to the bottleneck stability theorem, which says that if we have two functions f and g, and they have barcodes g sub I of f and g sub I of g respectively, then the bottleneck distance between their barcodes is at most the infinity norm between the two functions right here. And so this proof is done by transfinite induction on the cells of X, where f and g differ. So it's somewhat similar to the proof in like the Vines and Vineyards paper of bottleneck stability. We're just sort of updating the persistence pairing each time the cells differ. And it's done by transfinite induction, but really transfinite induction here is not that hard. The hard part is the limit case, which is what you would have to prove in the finitely generated case anyway. The hard part is the successor case, which is what you'd have to prove in the finitely generated case. we again get the limit case for free, essentially from the fact that the free functor is a left adjoint, and left adjoints can be with colimits. Yeah, so thanks for listening. Any questions?
Thank you very much. Let's all unmute ourselves so that we can clap together for the speaker. And now, please ask your questions. Or maybe I have one while everyone is thinking what question they want to ask. Quite at the end, you said that you don't need matching to the diagonal because you anyway have the same complex. So I get that, therefore, you have the same number of persistence pairs. But couldn't it still sometimes be that you would get a better matching if you match one point to the diagonal and a point from the diagonal to a persistence point instead of matching them with each other? Like, I didn't get that part.
Yeah, sorry, I accidentally closed out my slides. Did not mean to
yeah,
do
you can
that.
just share them again.
Yeah. But yeah, that is a good question. And the answer to that question is yes, you could get a better matching by possibly matching points to the diagonal, but that's okay. Because if you sort of relax the condition on matchings to allow for, like, say, partial injections, like that's typically done with matchings, you're allowing a greater set of matchings. So the bottleneck distance you would get would be smaller. So you would still have this this result right here. You'd get a smaller bottleneck distance than this. So this implies that other bottleneck distance, or the sort of more traditional bottleneck distance.
Yeah, so you managed to prove that even if you don't allow matching to the diagonal, you get this result, and if you allow it, you get this result even more.
Yeah. Yeah.
Nice. Okay, thank you. Any other questions?
I'll ask a question, Alex. So I was curious if this relates, and if so, how it relates to sort of Q-tame persistence modules, or like persistence modules you get from Viator-Strips complexes of, I think it's like totally bounded metric spaces, right? So Chazal and collaborators show that you build a Rips complex on top of a totally bounded metric space, and you might get non-finitely generated homology at a particular scale. Right?
Yeah.
But if you look at a induced map where you increase the scale a little bit, you always get like a finite rank. And then they sort of use that. That's like a Q-tame module, and they use that sort of to define persistence diagrams, etc. So does that setup all sort of fit inside of your framework, and then your framework extends to even sort of other infinite CW complexes that don't necessarily arise in that way?
Yeah, to some extent. There is we are only able to do this over well-ordered sets. We can't do it over the real line. So that is a restriction that those other approaches don't have. But for the most part, the answer to your question is yes. This does extend, right? We don't need really any finiteness conditions at all. But we do need this well-ordered set condition. And you can always find like a well-ordered set that's sort of epsilon close to every single real number, right? I mean, you could just, or positive real number. Yeah, you could just take epsilon times the natural numbers, for example.
And then you sort of get a barcode in some sense, and it might have like an infinite number of bars.
Yeah,
that's fine.
Yeah.
I see. Gotcha. Whereas in the Q-tame setting, you don't get an infinite number of bars of non-zero length. I see.
Yeah.
Okay. Cool. Thank you.
Okay. Any other questions? Okay, then maybe let me end the recorded part here, and then we can still have questions in the unrecorded part. Thank you again so much for this very interesting talk.
Yeah, thank you.